Got here a question about operational amplifiers, and we look at these as the ideal features of an operational amplifier. So it's a very much simplified one. This comes down to really just remembering what these different things mean when we talk about them. And if it has an infinite bandwidth, that means that all the frequencies, all input frequencies, are amplified equally. Okay, so just remember what that is. Zero output impedance. Now, impedance is something which is very analogous to resistance. We talk about impedance more whenever we've got an alternating current or a current which is showing lots of changes or non-gradual changes. So, for example, whenever you discharge a battery, you would get a current kind of going in some way like that should be linear, in some way like this. Whereas if we've got any amplified signal, this is probably changing quite a lot. These signals in here are changing quite a lot. So what's more useful to talk about is this thing impedance. Now, the zero output impedance. So if there's no impedance on the output, apart from the resistance that we have there, that is because, what is meant by that is that there's no voltage drop in the output. So, when I say voltage drop, what I mean is, impedance can be represented in the same way as resistance. It's more often actually represented using this zigzag type symbol here. Should be a slightly better zigzag than that. But of course, whenever there is any resistance, there is some transfer outwards of energy, and so there's a voltage drop. You've got your EMF in, and it should be equal to the voltage drops of these summed together. So that's the zero output impedance. So the reason I'm explaining the term impedance is because if you get a question like this, you'd be like, you can kind of reason out the meaning of it based on that. Whereas infinite bandwidth, it's a bit more difficult to sort of reason out this from the term infinite bandwidth. Anyway, what we've got here is a non-inverting amplifier, and when you look at the syllabus, you'll notice there's quite a lot of features of a non-inverting amplifier that you need to basically remember. Okay, now when we look at gain, this next question is asking about the gain of the amplifier circuit. When we look at the gain in its simplest terms, we look at it in terms of V out, which is equal to the gain multiplied by the difference of the inputs. So you'd say, V plus minus V minus. Okay, for this kind of one, for a non-inverting amplifier, there's a particular equation that they use for gain, and it's related to the resistances, these two resistances. Okay, so what we've got here is this is RF, and that is the resistance in the feedback loop. And here we've got Rin, that's the resistance close to the input. And so it's asking us to calculate the gain of this. This detail isn't particularly relevant. Calculate the gain of the amplifier circuit. So from that, gain is equal to 1 plus the ratio of RF to Rin. And basically that is for 2 marks. You remember this, and then from that it's pretty darn easy because RF is 4,000 and Rin is 800. So it's just 1 plus 5, which is equal to 6. Okay, there's no unit because it's just a factor. Okay, it's just a multiplier. So when we go over here, determine the value for V in for which the value of V out is plus 2 volts. And this brings us back to that original definition of gain, because the gain is equal to the ratio of V out to V in. Okay, so to V in. Okay. So that equals 2, 6, which is just 0.33. Weirdly, the mark scheme always just gives this to 2 significant figures, and that seems to be fine here, I guess, because it implies it doesn't really imply that it's 3 recurring, but anyway. We say, and then the next one, state the maximum value of the output potential V out. A general point on questions which say state is that what you should be able to do is just look at something and see that's what it is, or kind of figure it out just from what's in front of you. You shouldn't need to do any calculation to get a state question, okay? And the maximum potential V out. Well, if you remember the fundamentals of operational amplifiers, the maximum that any V out can be is related to these, okay? So it's either plus 5 or negative 5, okay? So our maximum in that case is just 5 volts, okay? Then, where are we at? Oh yeah, 3. Okay, so then the next bit, when the op amp is saturated, the potential difference across the LED is 2.2 volts. Calculate the minimum resistance of resistor R so the current in the LED is limited to 20 milliamps. Okay, so now what we can see from this question, well, it tells us that the current must not be greater than 20 milliamps. And there's another fundamental thing, because we're interested in resistor R, so that means that the this is 20 milliamps, and of course it's the same current throughout there. So it's just slightly tricky to do with the diagram on the other page, but we'll work it out. So when the op amp is saturated, the potential difference across the LED is 2.2 volts. Oh yeah, okay. So when it's saturated, that means we've got this maximum output. Okay, so we've got our, I'll draw the diagram here. We've got our LED, we've got that resistor R. Okay, and so what we should remember from GCSE and from year 12 is that because that's connected in parallel to the other parts of the circuit, then what we will have is a V, a potential difference across this of 5 volts. Okay. What that means is that the potential difference across the LED, like it tells us, is 2.2, which means, of course, the potential difference across this is 2.8. Considering that, we need to find the resistance, and then we just very simply take that as R equals V divided by I. So we know our voltage 2.8, and we know our current 20 milliamps. Save yourselves a bit of time and messing about with decimal places, just 20 times 10 to the negative 3. And from that we get something quite big, divided by 2.8 times 10 to the negative 3, and we get 7,142. That seems quite big. Yeah, because for some reason I did, I did something really dumb there. Well, lucky I did a sense check. Lucky I'm used to doing that, because for some reason I just did 20 divided by 2.8 times 10 to the negative 3. Must be stage fright. Divided by 2.8 times 10 to the negative 3. Oh my, look at what's going on. What's going on? 2.8 divided by 20 times 10 to the negative 3. 140. 140 ohms. There we go. Okay. So this is kind of another thing about the design of electrical circuits, is that LEDs, there is usually quite a low limit to the amount of current they can handle, and so they're normally connected in series with a resistor to protect them. So resistors are useful in loads of things, but one of them is protecting some components in the circuit. Anyway, there's that question.